We'll talk about SVE and SVE support in GNU and LLVM toolchains today, and I'll try and give an update of where we are, and also try and give you a roadmap of when do you expect to what extent support in the next months and quarters. Yeah. And any questions, we can have it at the end. Just passed. So SVE, just a quick recap, it was introduced in 2016, if I'm not wrong. And it was mainly as an HPC extension. It brings in some interesting features which are never there before. Gather, load, scatter, helps in vectorization. You have Perlin predication, again, helps in AutoVectorization by compiler. Predicate-driven loop. Moving on, we have the software managed, the first faulting load feature, which again helps in if you want to write optimized string functions and stuff, it's really good. And then we have the extended floating point. So in general, it was an optional extension. It was added to support a new use case, which was HPC, which was never there in a base ARM architecture. And as previously explained, Fujitsu decided to pick this for their post-K machine, and that'll be one of the first hardware to support SVE. Since 2016, we've been trying to add support into multiple toolchains. It's complex because it's new, it's variable size and stuff, so it's taken quite a bit of time, and I'll give an update over it. SVE registers was already talked about in the previous one. I won't go much in detail. The main thing which was introduced 6 months ago was what we call SVE2. It's an advanced architecture feature. It's not part of any announced architecture variant of ARM. So it's not part of 8.6, for example. And the reason we announced it early enough is to ensure the software ecosystem gets ready, because it's, again, intrusive, and it'll take some time before all the ecosystem is kind of ready. So the SVE, it is built on SVE foundation, and SVE2, you would expect. It's mostly SVE, but the main difference is it's on par with Neon. So the big issue, big challenge with SVE is it doesn't have the Neon style operations, whereas SVE2 brings it on par with Neon. What that means is whatever that would use Neon instructions now can completely use SVE2. There is no need to use Neon, so compilers can just generate SVE2 code. It has all the benefits of SVE plus all the features of Neon. So that's the main advantage. So you would expect, because of that, now a lot more options beyond HPC open up. So you have DSP, area, codecs, and computer vision, game physics. It's a whole bunch of new areas open up, which was not possible before. So that's why we think SVE2 is a really interesting extension, which brings SVE to the mainstream. Yeah, it's not just a special use case of one supercomputer or HPC anymore. In terms of details, you have the DSP instructions, which are traditionally, so you have fixed width, complex dot product, and those kind of things. But there are some other new features that have been introduced as well. You can see the applications in the bracket of which feature is kind of aimed at which application. There are some parts of it which are optional, kind of brown, red in this. So these are not mandatory for every SVE2 implementation. It's an optional thing, but rest of the features, most of it is kind of an enhancement as far as SVE2 is concerned. So a whole bunch of features, as you can see. Now, typically, what does it mean when we say SVE2 support has to be there in a toolchain? Yeah. So architecture spec comes out. This is the registers. This is instructions. This is the ISA. What do we need to do? So you have on one side, you have assembler and disassembly support. That's one of the basic things. The first thing that happens in any toolchain support on LLVM, you have it's directly go to LLVM project. On GCC, it goes into the binutils project. And then we have what's called as an intrinsic. So in ARM's parlance, it's ACLE. It's a C language extension. It allows you to write low-level code, which is typically not automatically generated by the compiler, without having to go through the register allocation and scheduling and all those issues. So typically you would see that when somebody implements hand-coded library functions, they prefer to implement an intrinsic, which allows you to kind of write once, and then the compiler will do the tuning for the specific microarchitecture. So that's the ACLA bit. The final bit is the AutoVectorization, which in some sense what it means is compiler can use it on its own, right? You don't have to tell anything. You just write your C code, C++ code, whatever code, and it automatically picks up and uses the right instructions. Now the last AutoVectorization is where SVE and SVE2 benefits will be realized over a long period of time because compilers can now have the fundamental infrastructure to use. Yeah. Now, which components need to be supported? You have the compiler, disassembler, assembler, debugger, and the libraries. So broadly, a tool chain has these many components. As you might expect, they are supported at different times because you'll have to start the assembler, disassembler first, and then move further. So let's look at GCC in particular, the GNU toolchain. For assembler, disassembler, SVE and SVE2 is completely supported, right? So when GCC 9 comes out, GCC 10 comes out, May 2020 or around that time, you will have a full support for assembly, disassembly in that toolchain. If you're interested, you can go and get a binutils version now, which I think is about to be released or already released. So then that also has your SVE and SVE2 full support. The intrinsics bit is where it becomes challenging because there's a new concept called Sizeless Type that needs to be introduced into the language. There's a lot of contention of how it should be done. So it's taken a long time. It's not supported in GCC 9 right now. We planning to get it in GCC 10, but it's we'll have to see what the upstream maintainers say. On the compiler, AutoVectorization side, SVE support was there as GCC 8, which is like 2 years ago. Yeah, even we've added more improvements. So as we get more feedback, we add more improvements, more AutoVectorization cases. More is being planned in GCC 10, and this we would expect it to happen over many years, right? Once the real hardware comes, then you'll find some corner cases. You'll have to improve it. For example, even now we are doing a lot of optimizations for Neon, even though it was introduced almost a decade ago. The SVE2 AutoVectorization, once the binutils now it has a support, it'll get in again. So, like I said, if you pick a tool chain of 2020, you'll have basic SVE2 support, AutoVectorization, and nearly full SVE support. The only question is how much of support we can get intrinsics. So we should know in a month or so when the stage 1 window kind of closes. Debug support is now there in GDB 8.2, so it's fully there. And the library support is the interesting bit, which we plan to, so this kind of needs hardware first. You can't just implement these routines in isolation because you will not know how the hardware microarchitecture has been implemented. So we plan to add these routines first into what the project we call ARM optimized routines. There's a talk later this week by Joey, which talks about the ARM optimized routines project. It's a conveniently licensed in the sense it's a license. The license allows that you can take a routine from that project into anywhere. You can take it into your commercial tool chain, you can take it into glibc, you can take it into LLVM, libc, it doesn't matter. So it'll go there. You should expect that we will work on the routines in the upcoming year or so. Any questions on GNU toolchain? Yeah.
Actually, I wasn't asking about GNU, but what about CLAN?
That's the next one. Yeah.
Oh, okay.
All right.
And Fortran.
Fortran.
Yeah, because that's really big in HPC environment.
Yeah. Okay. Okay. I can answer that. It's not there in the slides, but I can answer that separately. So the oh, sorry. Yeah.
We can talk about then shape or hardware
It's, like I said, it's not even part of a standard architecture. So all I can say, it's coming. It's not there yet, and you'll have to see for partner announcements of when they announce. The only publicly, I think, right now that's been announced is the SVE hardware, which is A64FX, with details have been announced, and it's expected to be available later this year or next year. But SVE2, no information right now, which is publicly announced. So moving on, LLVM toolchain. I'll quickly pass through the ones. Assembly, disassembly is fully supported in LLVM 9. Yeah, so it's not an issue. Intrinsics, Clang has the same issue as GCC, so we're trying to address both those front ends at the same time, because one might have feedback which is valuable for the other. AutoVectorization is an interesting challenge, which I'll explain in the next slide. In LLVM, it's been much more difficult for us to get support because it needs some core IR level changes, which the community has been very careful into meddling. So it's been a bit of an interesting challenge there. But we have made significant progress, as you can see, because now the core IR has finally been updated to support some what we call scalable vector, which is your variable kind of vector support. The library, same story as the ARM optimized routines. We'll just put it there, and then it can go into either of the tool chains. Now, in terms of where the challenges are, now this is a kind of a diagram my engineering team put as to how much is left and how much has been done. Yeah. So just take some time to explain. What nearly looks like white, but it's supposed to be gray, is complete. Right. So this one took 2-ish years, and there was a lot of pushback because it fundamentally changes its SVE IR, which is the LLVM IR, with, I think, RISC-V having similar kind of requirements and the hardware being nearly available. So there was a final push, and it got accepted. So that's moved. And then we have the calling convention, which is also finished, and a bit of intrinsics that's been finished. There are 3 or 4 items, as you can see, which is in progress. The interesting bits are the discussion underway and needs discussion. So the needs discussion means it'll take longer than what we would like. And discussion underway is we made some progress, and it's likely to finalize in a decision when move forward. So for example, the optimization passes, and the constant V-scale and global SLT, those things are going to be interesting in the next 6 months. If you watch LLVM dev mailing list, you'll see these conversations right now going on. So anyone who wants to know when it is done, it's a whole bunch of moving blocks that needs to be finished, and eventually we'll have AutoVec and ACLE. In terms of ARM and ecosystem, what we are watching is there are 2 main things we want to get. One is the Sizeless Type, which allows intrinsics to be written. You would expect with something like SVE that there will be libraries written with intrinsics, so that's kind of important. The other one is some of the needs discussion to progress. And once that progresses, then it'll be on par with something like GCC toolchain, where it does basic AutoVec, and then we can keep improving it. Yeah. To answer your question on Fortran, Fortran has a Flang frontend, and that uses LLVM as a backend. So right now, the only way you can do that is you'll have to use the ARM commercial compiler, because we have added these changes into our LLVM downstream branch, and we have a Flang which uses this. So the thing is, we don't have a Fortran intrinsics, or nobody writes Fortran intrinsics. So it's not like you'll not write an assembly language kind of thing in Fortran. Only thing is it needs to be mapped onto the right level of SVE. So it's just a LLVM. So once LLVM has full support, you would expect the new Fortran project, as it's called, F18, to automatically have that support.
Is ARM also making math libraries and things like that for HPC systems and providing them?
Yeah. So there are 2 kinds of math libraries you have. One is the traditional glibc kind of math libraries, which we'll put into the ARM optimized routines. And then there is HPC specific, which is the matrix multiplication, BLAS, LAPACK kind of libraries. So those are, I think it's being done in 2 parts. One, there are some open source projects which are really good, like FFTW, for example, which provides FFT. So that's being upgraded to have SVE support. and then there's a commercial binary. So one of the fundamental differences between something like HPC and a non-HPC is HPC is a very expensive machine. They want supported somebody that can call toolchain. They don't want free alone because there's a risk that you don't want the big machine to be idle because you don't know where the problem is. So commercial libraries are kind of a necessity, not even an option. You have to have it before you can have a supercomputer. Any other questions on LLVM or GCC? If you ask my engineering team, they would like it done now. But it's been going on for some time. So the way I would say is, I think it kind of depends on few key parts. So depending on how this goes, if this goes well, the sizeless property goes well, then you should have intrinsic support in the next 6 months, right? Like LLVM 10, we should have it. That's what we're internally aiming for. As AutoVectorization is an ongoing thing. So LLVM 10 will have some, LLVM 11 will have more, and so on.
Okay, so how can I validate this? Is there a simulator out there that provides?
It's a good question. So in terms of other projects and tools, right, it's just leading to the next one. So you have QEMU, which supports full SVE today. So you can run SVE binaries in a QEMU, which runs on Linux. And Linaro gave me an update saying, I think Maxim's team is looking at how they can add SVE2 support. So you should see more progress there soon. Valgrind is another tool that typically is required, and that doesn't have, I think it doesn't even have proper 8.x support today. So we need to add a lot of things there before we get to SVE, but finally we have a Linaro assignee looking at it. So things should move there, which is a good thing. The last bit, which is DynamoRio, which is ARM's kind of version of PIN. It's an instrumentation tool, and that has partial support, and ARM directly adds support there. If you're interested in kind of a dynamic analysis, then that's an interesting tool to look at. Yeah.
So in HPC environments, we often work with security classified information, and one of the things is you could probably use this for encrypto on the fly kind of stuff. And you need that in the kernel. There's a crypto API. Has that been looked to implement that?
In SVE?
Yeah.
I personally don't know, but I can find out and let you know.
Because they use that also for like the ZFS file system. A lot of sites have it encrypted in compression. And
so I'm just covering the tools, but obviously libraries will make use of it, underlying libraries as well.
I was just wondering if anybody was looking at doing that kind of work at ARM.
So I don't know, but if I were to hasten a guess, which I shouldn't considering it's getting YouTube recorded, but I think the thing is, till hardware comes along, these kind of optimizations will just wait. So once the hardware comes along, it'll make it much faster. So I can get back to you on that. On the commercial tools, we have something called an ARME, which is a user space emulation, which is equivalent of a QEMU in some sense. But it's built on DynamoRio, so you can write some plugins, analyze memory accesses, instruction count, that kind of things, much easier than QEMU, which is mostly built around emulation. And the commercial compilers, like I talked about for HPC, so the last one is the HPC compiler, which is the Linux user space compiler, so that supports SVE today. Any other question? Does that answer your question? Yeah. Okay.
Yeah, but I mean, the most interesting for SVE, in my opinion, is having something that you can validate the performance.
Yeah.
Right. I mean, you can generate the code once the compiler has basic support.
Absolutely. I cannot disagree more. Right. So we've been waiting since 2016 for real hardware. Right now, it's a lot of what we think should run fast. So in a compiler, for example, our goal right now is to make sure it vectorizes. Now, once the real hardware comes, we'll see how effective is that vectorization in terms of speed, right? So if you can use scatter gather, you can use all those fancy features, but does it really make an impact in terms of performance is something to be seen.
Is there any performance model in the simulators?
So in the ARME and the DynamoRio think it's not a performance model, but you can estimate things like, okay, how many memory, where the memory accesses were, what kind of SVE instructions were used. So it's still at a, not at real hardware. So there's no way of knowing how fast it will be on a real hardware or what our performance is going to be. So it's going to be an interesting time next 1 year. So you'll see in my summary as to just jumping further, right? So the way I would phrase it is we made sufficient progress to get started, and so which means that you have an assembly, disassembly, and all that. Once real hardware starts turning up, I'm looking at anyone from Fujitsu here. Once real hardware starts turning up, this thing will move fast. Yeah. So right now it's a lot of heuristics, and one performance model will tell a number, another performance model tells opposite number. It's very hard for a compiler or a library guys to decide what's going on.
Do you have any performance numbers with the hardware you have, the prototype?
So we don't make hardware as a company. So I can safely say that we are also waiting with an ARM for real hardware. So once that comes, it's the Fujitsu machine, right? So that's the only announced hardware right now.
Are you working with any reference board manufacturers to come up with a reference design? Because
Yes, that's a good question. Is there going to be a SVE reference board anytime soon? I would love that, but I so far have not heard of any such plans. The expectation is it's going to be a remote machine where you can just log in because it's a server and you run your SVE. I think there was a supercomputing center in US announced that they will have a machine next year. Any other question? Yeah.
So you mentioned that You mentioned LLVM took longer to get the AutoVectorization support in. So what's the difference between the GCC and LLVM IR that made it easier to do in GCC? Because I always thought LLVM was the more evolved design for this sort of thing.
So this is what I have understood. Okay, it might be completely a product manager view, marketing view. So Richard Sandiford is our GCC SVE maintainer, and I think he knew how to do it properly in GCC, and considering his influence, it was much, I think, much easier path. But even there, it's not done because we are struggling with the intrinsics, so because we need community acceptance there. Now, in the LLVM side, with MLIR coming in, there's a lot of discussion of whether the low-level IR is the right place to add these kind of things, or there should be an intermediate, something that's above, before you lower into the all the way. And that took 2 years to decide that we will finally let you inside or not. Because there's a good case to be made that this is not necessary at the lowest level IR. You introduced something like a high level IR, which then lowers into the final IR. But that fundamentally makes C and C++ support very hard, because they directly lower into the low LLVM IR. Okay, so that's been the challenge, yeah. Any other questions? Okay, thank you for attending this talk. If you have any questions, you can get in touch with me over email. Otherwise, thanks a lot.